Hello and welcome to GCSE Physics Explained. I'm going to show you how to answer some exam style questions from SP1 and SP2, which are Edexcel units. But basically this will do for any exam board because all exam boards ask students about motion and forces. These questions are relevant for both the triple and combined science. The only questions you'll see here from SP2 with regards to the triple content is about braking distance and energy. I'll let you know when I get to that question. Question 1. Figure 12 shows a skier on a slope. The skier travels down the slope with a constant acceleration. The speed of the skier is measured at points P and Q. The table in figure 13 shows some data about the skier making one downhill run. Right, so they're showing you the acceleration, the speed at P and the speed at Q. Calculate the distance from P to Q. Use an equation selected from the list of equations at the end of this paper. Right, let's have a look and see what we've got. So we've got acceleration. Let's call that A, because it is A. Speed at P. Right, P's at the top of the slope, so we'll call that U, which is the initial velocity. And the speed at Q, well, that's the velocity at the bottom of the hill, so that'll be V, the final velocity. And it's asking us to calculate the distance. So distance equals question mark. Now, what equation do you know that connects these three things? You'll be given the equation in a sheet at the end of the paper, and it's this equation you need to get. V squared minus U squared equals 2AX. Now, distance in this case is referred to Edexcel as X. Now we've got to rearrange that then. So therefore, these three little dots mean therefore. So X is going to equal V squared minus U squared divided by 2A. Let's put the numbers in. And that equals 86.37, so we'll round that up to 86.4. Part 2. Calculate the time taken for the skier to travel from P to Q. Right, so we're after the time, T. Now what equation do you know that's got A, U, V and T in? Right, well it's this one. Acceleration equals V minus U divided by T. So final velocity take the initial velocity divided by time. Right, let's rearrange that. So therefore, time equals V minus U over A. Pop the numbers in. That comes out as 5.46 recurrent. So we'll just round that up to 5.5. Question 2. A car travelling at 15 metres per second comes to rest in a distance of 14 metres when the brakes are applied. Calculate the deceleration of the car. So deceleration, that's the same as acceleration. So that's our question mark. The car was travelling at that speed, so that's our initial speed U. And it comes to rest, which is our final speed V. Rest means it's not moving. And we've got a distance D or X of 14 metres. We'll use the same equation as before, but we'll rearrange it in a different way. Put the numbers in. And that comes out as 8.0. Question 3. The diagram shows a girl swinging a rubber ball in a horizontal circle above her head. In which direction does the resultant force act on the ball? Put a cross in the box next to your answer. Well, the only way that the ball can go in a circle is if there's a force pulling it in towards the centre. So that's what we're looking for. So the answer is D. Part 2. State the name of the resultant force acting on the ball. Well, that particular kind of force that pulls things to the centre of a circle, we call it a centripetal force. Gravity is also an example of a centripetal force. In this case, however, it's tension in the string. Suggest what would happen to the ball as the girl gets tired. Right, well, if she stops swinging it as hard, the ball's basically going to start to drop down a little bit, and it'll also move in a little bit. So the string would sort of fall down to here. You have to be careful it doesn't hit her in the face. And yeah, the ball will be there. So it's gone a little bit lower. If she's getting tired, the ball won't swing as fast. That's why it's dropped. If it's not swinging as fast, that means the kinetic energy is less. And if it's physically lower, that means the gravitational potential energy is less as well, because it's not as high as it was. Part 4. The girl lets go of the string and the ball hits a wall. The collision is not elastic. Right, that means that energy is going to get lost. Explain what happens to both momentum and kinetic energy when the ball hits the wall. Well, if it's not elastic, that means that energy is going to be lost. So that means kinetic energy is going to get lost from the ball. It'll get turned into sound as it hits the wall. And we need to mention about momentum. Well, momentum equals mass times by velocity. The mass of the ball will still be the same size, but if it's lost kinetic energy, the ball will not be moving as fast. Its velocity will have decreased, which means the momentum will have decreased. Question 4. Figure 13 shows two objects Q and R before and after they collide. Right, so Q's a big ball, R's a little one. R's not moving before the collision, only Q is. After the collision, they're both moving. The arrows show the direction of movement of the objects. The arrows are not to scale. Explain how momentum is conserved in the collision. Use Newton's third law and Newton's second law in your answer. Newton's second law can be written as force equals change in momentum over time. Right, so they're basically telling us that momentum is conserved in the calculation. So let's write that down mathematically. Right, let's make sure that the examiner knows that we understand that momentum is mass times by velocity. Might get a mark for it. Right, let's put some bullet points down here. So hopefully if we get 6 bullet points, that'll be our 6 marks. Right, Newton's third law is about actions and reactions. So basically, when Q bumps into R, Q is going to put a force onto R. Now at the same time, R will put a force onto Q. But remember, forces are vectors, which means they've got size and direction. So the force that R puts onto Q will be opposite in direction to the force that Q puts on R. And we know it's Newton's third law because two different objects are involved. I've got a nice little video to do with that. That explains Newton's third law if you need it. Right, look at the size of Q. It's much bigger than R. So if something big bumps into something little, R is going to move off faster than Q will, as Q transfers some momentum to R. Now that is 6 bullet points, so hopefully that'll get us 6 marks. However, I haven't used this equation, so just in case, I'd better use the equation here. Now, as I said before, the force of Q on R will be the same size as the force of R on Q, but they'll be opposite in direction. The way we write that mathematically is like this. Now, as you can see, they've gave us equation for the force, so we can expand on this here. Now, the time taken for the impact is going to be the same. So if it takes, a 100th of a second for Q to bump into R, that basically means it's going to take 100th of a second for R to bump into Q. So we can get rid of time. Right, you'll definitely get 6 marks for that, so we'll just leave it there. Question 5. Answer the question with a cross in the box you think is correct. If you change your mind about an answer, put a line through the box and then mark your new answer with a cross. The force that keeps an object moving in a circular path is known as the... Right, well, we've had this before. It's the centripetal force. There's 3 centripetal forces, by the way. Friction, tension, and gravity. I've got a nice little video on that if you want to watch it. Question 6. Describe how the student could extend the investigation to determine the average speed of the trolley as it rolls back down the track. This exam style question is part of a bigger question. What we're looking for here is how to get the average speed of something. So always base your explanation on a calculation. So the calculation for speed, the average speed equals the total distance divided by the total time. To increase the accuracy of whatever it is you're trying to work out, it's always best to try to make, in this case, the total distance as big as possible and make the total time as big as possible, and that'll help to reduce any human errors because of reaction time. Or to get rid of reaction time completely, use light gates. Question 7. Which row of the table is correct for both force and velocity? Right, they're asking about scalars and vectors. Well, force is a vector, it's got both size and direction, and velocity is a vector as well, both size and direction. So the answer is D. Question 8. A firework rocket contains a solid fuel inside a cardboard tube. The burning of the fuel creates a thrust to propel the rocket upwards. Scientists can refer to several different quantities when describing the motion of the rocket. Only one of these quantities is a vector, so has both size and direction. Complete this sentence using one of the words from the box. The vector quantity is, it'll be force, because none of them three involve a direction. Part 2. Before the fuse is lit, the total weight of a rocket, including fuel, is 0.7 newtons. So that's the weight, is it? Let's write that down. The gravitational field strength is 10 newtons per kilogram, right? That's our gravity. I would write down what you know as you know it. There's your exam tip for today. Hey! Complete the sentence by putting a cross in the box next to your answer. The total mass of the rocket, including fuel, is... Right, total mass. Okay, so we've got the weight, we've got the gravity, we are looking for the mass. What equation do you know that connects weight, gravity and mass? Well, it's this one. Weight equals mass times by gravity. Let's rearrange it. So therefore, mass equals weight over gravity. The weight is 0.7 newtons. And the gravity is 10. So that means the mass is going to be 0.07. So the answer is B. Part 3. There is a resultant force on the rocket of 0.5 newtons upwards when it takes off. The arrow on the diagram shows the size and direction of the force of gravity acting on the rocket when it takes off. That's that thing pointing downwards then. Add another arrow to the diagram to show the thrust produced by the burning fuel at the time the rocket takes off. You should label the arrow and the size of the thrust. Right, well if it's got a resultant force of 0.5 upwards, that'll mean that when you take this downward force away from the upward force, the answer has to be 0.5. So basically the size of that thing is 0.5 newtons plus 0.7 newtons, which is 1.2 newtons if you're clever. Remember, a resultant force is the force that you get left with once you take opposing forces away from each other. So that force is going upwards, that force is going downwards. Take the bottom force away from the top force, and then you'll end up with the resultant force of 0.5 going upwards. Question 9. Answer the question with a cross in the box. Right, we've had that before. The work done to bring a car to rest is given by the equation work done equals braking force times by braking distance. Which of these graphs is correct for the car if a constant braking force is applied? So, constant braking force. Right, let's take that equation and rearrange it to find braking force. Equals work done over braking distance. And what they're saying is that this braking force here has to be constant. Now the only way that you can keep this constant is if every time the work done increases, the braking distance increases proportionally. Right? So what we're looking for is we're looking for the relationship between work done and braking distance to be proportional, which basically means a straight line going upwards through the origin, 0. So the answer is A. Question 10. Explain one way the students could improve their procedure to obtain a more accurate value for G. Right, once again, that is a part of a different question. It's actually part of this question. So let's answer question 11 first, and then I'll go back to 10. And you'll see how it makes sense. Two students try to determine a value for g, the acceleration due to gravity. They measure the time t for a small steel ball to fall through a height h from rest. They measure t to be 0.74 seconds using a stopwatch. They measure h to be 2.5 meters using a meter ruler. Calculate a value of gravity from the student's measurements. Use the equation. So sometimes they just give you a random equation. Just use it. Don't worry too much about it. Just put the numbers in. So in order to work out a value for gravity, it's 2 times by h. Now they said that h was 2.5. So that's 2 times by 2.5. And we need to divide it by t squared. So time t was 0.74. So 0.74 squared. And whatever answer that is, that's going to be our value for g. And that comes out as 9.13. They record the time t for 2 more drops from the same height. The 3 values for time t are that, and that. Calculate the average value of time t to an appropriate number of significant figures. Right, well they've used 2 significant figures, so we'll do it to 2 significant figures as well. To get the average, just add that, and that, and divide it by 3. Do any of them look like an anomaly, so I've got to leave it out? Nah, they look fair enough. So that's 0.746 recurring. And we'll do it to 2 significant figures, so that's 0.75. Now we'll go back to question 10, and this will make sense now. Explain one way the students could improve their procedure to obtain a more accurate value for g. Right, well in order to get g, we'll do 2 times by the h and divide that by t squared. So just like before, we could say that we could increase h, the height, because then that would allow you more time to start and stop the stopwatch, which would reduce inaccuracies due to reaction time by human error. And the other thing that g depends on is time. Well, why not just reduce human error completely by letting a light gate and a data logger record the time for us? What I mean by reaction time is the human reaction time is about 1/4 of a second. So if you're going to drop a ball, you might not start your stopwatch at the exact time that the ball is dropped. And you might not stop your stopwatch at the exact time when the ball hits the floor. Light gates are basically where the ball would pass through some light and it would break the light, and that would start the stopwatch. There's a beam of light there. And then at the bottom, you'd have another light gate at the bottom. And when the ball breaks that light, it stops the stopwatch. So you get the time taken to go from that position to that position, which would also be the height between there and there. Question 12. Some students investigate a model of the craters produced by meteorite impacts. They drop balls into a tray filled with sand. They use 6 balls with different masses. They drop each ball from the same height. Same height, different masses. Which one of these graphs show the relationship between the gravitational potential energy, GPE, of the balls and their mass when they are all at the same height? Okie dokie. Right, let's base our explanation on the calculation. So the calculation for GPE equals the mass times by the gravity times by the height. Right, well, gravity is a constant. It's always 10 on Earth. And also height in this particular example is also a constant. So that means that the gravitational potential energy is proportional to the mass. That wiggly sign there means proportional. Right, since they've plotted gravitational potential energy up the side and mass along the bottom, basically as one thing gets bigger, the other thing needs to get bigger proportionally. Now, we've already had a question about that before. You represent a proportional relationship on a graph with a straight line. So A is correct. Part 2. Describe how the energy of a ball changes as it drops toward the sand. Right, so you've got the ball, which is quite high at first. So the height is large, and then the ball is going to be lower as it falls. So basically, the gravitational potential energy at the start is very big, and then as it falls, the gravitational potential energy is getting smaller. So gravitational potential energy is getting less. Now, energy can't be created or destroyed, it just gets transferred from one form to another. So where's the GPE gone then that we've lost? Well, the ball starts to move faster and faster as it falls. So kinetic energy is increasing. And because of the law of conservation energy, the total amount of energy would remain constant. So basically, we'd easily get the 2 marks. We'd even get 3 if they changed this into a 3-mark question. Question B. This photograph shows the sand after several balls have hit it. It looks like the moon. The students read this information in a textbook. When work is done, energy is transferred. Now, this is triple content. So if you're only doing the combined exam, don't worry too much about this bit. Well, don't worry at all. Explain how work is done when the balls impact on the sand. Right, once again, ladies and gentlemen, let's base our explanation on the calculation. So the calculation for work done. Right, well, work done equals force times by distance. So basically, there is going to be some work done because the balls are applying a force onto the sand, and the sand is moving a distance as represented by the big dents in it. So that's your answer. And if it was worth 3 marks, well, once the balls land, they're not moving, are they? So kinetic energy of the balls are being transferred. That's what it said. Work is done if energy is transferred. When one ball hits the sand, it has a velocity of 6.2 meters a second. So that's our V. It has a momentum of 0.46 kilograms meters per second. That's P. They use P for momentum. Calculate the mass of the ball. So M equals question mark. So we've got momentum, P, equals mass times by velocity. Therefore, rearrange it to get M. Mass equals momentum over velocity. So that is 0.46 divided by 6.2, which is 0.074 kilograms. You know the mass is going to come out in kilograms because it was given to you in kilograms here. Part 2. The ball takes 0.17 seconds to come to rest after it hits the sand. Calculate the average impact force. Right, well, impact force equals the change of momentum divided by the time taken for the change. So the momentum, basically, it goes from 0.46 down to 0 because it's coming to a rest. So that means that the change was 0.46 and it's took 0.17 seconds for the change to happen. So that's 2.7. Question 13. A student investigates the relationship between force and acceleration for a trolley on a runway. Figure 12 shows some of the apparatus the student uses. Part 1. Describe how the student could increase the accelerating force applied to the trolley. Easy peasy. Let's put some more weights on this end here. Part 2. Describe how the mass of the moving system can be kept constant. Right, this always confuses students. The moving system is basically anything that's moving. So that's the weight hanger, it's the string, and it's the trolley with the card. Now, we need to keep the mass constant. Now, this is the thing, right? If you are gonna put some more mass on here, put some weights on here, it's like, well, where did those weights come from? What the picture didn't show at first is that there should be some masses on here, and whatever you put on here, it has to come off the trolley. I guess another way of saying that would be like this. Because then the mass of the moving system's kept constant. Part 3. Explain how the student could improve the procedure to compensate for the effects of frictional forces acting on the trolley. Right, if you're going to get an accurate value for the acceleration, we need to make sure the trolley's not experiencing friction. So what you do, take the weight hanger off, right? Disconnect the string from the trolley. And then if you just raise this little thing here, it's actually a ramp, right? They haven't labelled it ramp, otherwise you'd be able to answer this easy, wouldn't you? So if you just raise that ramp so that this trolley, when it's not connected to anything, just starts to roll, then basically that means you've got rid of frictional forces acting on the trolley. Question 14. Figure 11 shows an object moving in a circular path. Draw an arrow on figure 11 to show the direction of the force that keeps the object moving in a circular path. Well, by now you should notice that we're getting similar questions coming up. All these exam style questions have been taken from different exam papers in the past. They just sort of use the same questions or similar questions year after year. So it's important to understand how to apply the knowledge that you're learning in the lessons. So that's the centre. The arrow will be pointing towards the centre. Part 2. The object in figure 11 is moving at constant speed. Explain why it is not moving with constant velocity. Right, speed is a scalar. It has only size. It doesn't depend on direction. Whereas velocity is a vector, so direction is important. Now, because this ball is constantly going in a circle, that means its direction is constantly changing. At the moment, you can see the direction's going that way. But if the ball was over here, then the direction will be going that way. Question 15. The symbol g can be used to refer to the acceleration due to gravity. The acceleration due to gravity g has the unit of meters per second squared. That's because it accelerates things down to the earth. G can also have another unit. Which of these is also a unit for gravity? Right. What equations do you know with gravity in? You know that weight equals mass times by gravity. So if we rearrange that equation to get gravity, right, the units for weight are newtons and the units for mass are kilograms. So that means that the units for gravity can also be newtons per kilogram, which is this one, C. And that's how you answer them type of questions. Question 16, the last question. The graph of figure 1 shows how the braking distance d of a car depends on the velocity v of the car when the brakes are first applied. An equation relating braking distance d to velocity v is this thing, d equals v squared over c. It's not important where it comes from, right? You get these type of questions quite often, just accept it. Where c is a constant, use the equation and data from the graph in figure 1 to calculate a value for c and give a unit for c. Right, the best thing to do in this kind of situation is we need to rearrange the equation to get c. Right, so c is v squared over d. Now they're saying that c is a constant. So no matter what value of v we take from the graph, if we square that v and divide it by the corresponding value of d, it should always come out as a particular number, i.e. a constant. Right, let's do that a few times then. Right, we'll take it when v's 15. And I reckon d is 18. So let's see what happens when we do that. So c equals 15 squared, that's our v, and we'll divide it by 18. Right, that comes out as 12.5. Right, let's take another value. So what if we do this 20? Right, what do we reckon d is? About 32. So let's try that again. That also comes out as 12.5. So we've just proved that c is constant and we'll give it a value of 12.5. Now the units. Right, we've got v and we're squaring it. So v's in meters per second. So meters per second, and we need to square that. So do you know that if you square the number, it also squares the units? And we've just taken d as it is, which is your meters. Right, let's expand out the brackets on the top. So that'll be meters squared divided by seconds squared. And then let's make sure, remember that the whole thing is being divided by the meters there. Now, that meters there can cancel out with one of the meters there. So that just equals meters per second squared. And there we go. It was Einstein who said, what's more important, imagination or knowledge? He said it was imagination, but we found out a lot more about the brain since Einstein passed away. We now understand that without all the background knowledge, you can't have an imagination. An imagination is bringing together all of the knowledge you've got to become like a creative problem solver. So I hope I've showed you how to take all the background knowledge that your teachers taught you and apply it creatively in order to be a problem solver and basically answer the questions. I'm going to create more videos like this, so hopefully it'll deepen your understanding of physics and help you to pass your GCSEs and fulfill your potential. Well, I hope that video was useful. Share the video with your mates. Subscribe to my channel if you want to learn more. Bang that bell all over the place. Smash the like button while you're at it. And apart from that, work hard, be nice, and bye for now.